Good morning, students. Now, the topic of our today's online classes is applications of Gauss's theorem. In this class, we are going to learn to derive expressions of electric field intensity due to a spherical cell using Gauss's theorem. So, let us consider a spherical cell of a radius r, on the surface of which charge q is uniformly distributed. Due to this cell, we have to deduce expressions for electric field at a point P, like this. Suppose here we have to find the electric field at a point P. Point may be outside, it may be at the surface, or it may be inside. So let us derive at each and every point one by one. So first of all, our first case is when point is at a point outside the cell. So here this is a spherical cell of a radius r having charge q uniformly distributed on its surface, and P is the point where we have to find the expressions of electric field. It is at a distance r from the center. So taking O as center and r as a radius, a concentric spherical cell is drawn as Gaussian surface. So here this concentric spherical cell is Gaussian surface, and at the point P we have to deduce the expressions of electric field. So first of all, let us consider an element of the Gaussian surface. The directions of area vector will be along this directions, and directions of electric field is along the same direction. Since electric field is the force acting on any positive charge, as the spherical cell is positively charged and charge is uniformly distributed, so if a positive charge is considered here, it is acted upon by force along this directions. So electric field will be along this direction. Now, as we know, here we calculate the value of the flux using once by Gauss's theorem and once by the definitions. So let us find the value of the flux according to definition. Since the value of the flux will be equal to E dot ds for this element, so total flux will be equal to integral of E dot ds. Now it is equal to E ds cos 0, which becomes equal to E ds. Now since the electric field is same at each and every point on the Gaussian surface, so E is constant, and therefore it is equal to E ds, or E and integral of ds for the entire closed Gaussian surface is equal to surface area, or 4 pi r square. In this way we find the value of the flux using the definitions. Now find the value of the flux using Gauss's theorem. So, but according to Gauss's theorem, flux is equal to 1 by epsilon naught the charge enclosed, and here the charge enclosed by the Gaussian surface is q. So flux is equal to 1 by epsilon naught into q, from 1 into E becomes equal to 1 by 4 pi epsilon naught, 4 pi epsilon naught q by r square. Now what will be the value of the electric field at a point on the surface? So when the point P is at the surface of the spherical cell, Then case 2, the value of E at surface, that is when R is equal to R, then E will be equal to 1 by 4 pi epsilon naught or Q by R square. Now let us find the value of E inside the spherical shell. So case third inside the shell, so this is our spherical shell whose radius is R and having charge Q on the surface, and P is a point inside at a distance R, and here we need to find the value of E. Again take O as center, R as radius, and consider a concentric spherical shell as Gaussian surface. On the basis of symmetries, you can say that the value of electric field, if there is electric field, it will be along this direction, and area element is also directed along the same direction. Now since d phi is equal to E dot ds, therefore flux is equal to integral of E dot ds. It is equal to E ds cos 0. It is equal to E and integral of ds, which is equal to E and 4 pi r square. It is the value of the flux according to definitions if we considered the value of E inside BE. Now, but according to Gauss's theorem, flux is equal to 1 by epsilon naught into charge enclosed. It is equal to 1 by epsilon naught I into 0, that is 0. Since there is no charge inside the spherical shell, charge is distributed only on the surface of the spherical shell, and there is no charge inside. So the charge enclosed by this Gaussian surface is 0. So from 1 and 2, E is equal to 0. It means no electric field inside the spherical shell. And if we draw a graph showing the variation of electric field with distance from the center, as there is no field, inside, so up to the surface there is E is equal to 0, and outside the surface it is E is inversely proportional to R square, and inside the shell electric field is 0. In this way we have learned how to deduce expressions of electric field intensity due to an spherical shell. Thank you.